Okay, so today we're going to expand on the idea of buffer solutions, and I want to give you some practical skills in that area. So, understanding how buffer solutions work is really just the Henderson-Hasselbalch equation. But let's say you want to go into the lab and make a buffer for whatever experiment. Say you're gonna grow some microbes, and those microbes are pH sensitive. You want to grow them in medium that's buffered, so that when they grow and their excretions don't change the pH and then kill off themselves and the colony. So a lot of the stuff for biochemistry and biology is it needs buffered solutions. So you're going to make a pH buffer. How are you going to do that? And so we're going to learn some of those skills today. Okay, so you can use titration equipment to do stoichiometry, and that's what we were doing with titrations, but you can also use the titration equipment to create buffers. That's probably the easiest way to make a buffer solution, is to have a target pH, select a particular weak acid that has a pKa in the range that you want that buffer to be, and then you place that known amount of the weak acid in the beaker and then start titrating with sodium hydroxide and just titrate it up to the pH that you want. Now, remember that we're not titrating to an endpoint, and so this is going to be a much easier range to hit. When you're in the buffer region, it takes a lot of base to move the pH just a little bit. And so it's pretty insensitive to, there's no endpoint where one drop sends it completely off scale. It's going to be in a real flat range of the pH. And so we can see that in the next slide. So in this titration curve for phosphoric acid, phosphoric acid, this one substance, because it has 3 protons, you could make 3 buffers with this particular species. Those flat regions of the pH curve are the buffer regions. So when you're halfway in between an endpoint, then you're in the perfect spot for those buffers. And so we could make a buffer solution with H3PO4 and couple that with the H2PO4 minus. And so those would be your C acid and C base for the Henderson-Hasselbalch equation. Okay, so that each equilibrium is that balance between the acid and its conjugate base. So you could buy sodium salts of each of these pairs, but that would probably not going to find it. I mean, you're going to find easily trisodium phosphate. So this one is real easy to find right here. But you're not going to find sodium dihydrogen phosphate. I mean, you might, but it's going to be really expensive because it's such a particular species. Trisodium phosphate is super cheap. And make it in bulk. You can buy it at Home Depot. Phosphoric acid, again, maybe a little more difficult to find. And so in that case, maybe you want to start with the trisodium phosphate in the beaker and then titrate with HCl. And so then you just run the pH from a high pH down to a low pH and you get where you want. So you could do it either way. You could start with all of the trisodium phosphate, and then when you're titrating with HCl, you're actually coming down this curve this way. You could stop right here and have a pH around 7.2, or you could keep going with this hydrochloric acid and stop right here and have a pH of 2.1. So whether you come from the right or the left, you can adjust that with the titration equipment. It will be a little tedious if you want to make a lot of it, because your burettes typically only hold 50 milliliters. And so if you're trying to make a whole liter of solution, you're going to be refilling that thing 20 times. And so that's kind of a hassle, but you might start with a couple of bulk solutions that you mix together, and then you titrate the last little bit to the pH that you want. But yeah, using the titration equipment to get to the exact pH, that's a great way to go. You can also buy buffers, and so you can buy these solutions of weak acid and their conjugate base pairs, and you can buy them in all different kinds of pHs. Here's a pH 4 buffer, pH 6. These are nice because they've been certified, and here's pH 9. You can buy these little packs that are really cheap. It's just the salts, and you just dump them in distilled water or DI water. stir and let it come to room temperature, and you've got your pH buffer. This is often a lot cheaper than labor cost. You say, well, you know, I can buy trisodium phosphate for dirt cheap, and I'll just make my own. But you know, time is money, and if you're spending your time, if it takes you a couple of hours to make the buffer, whereas you know your hour of labor is more expensive than a little bottle of pH 6 buffer, then it makes sense to just buy the buffer solutions. So let's look at this, and this is right the bulk of today's activity. This is a table of several pKa values for the different acids. And so that pH range is the range of pH values over which that buffer system works effectively. That it's going to be centered around the pKa. So whatever you find here, these pKa values, these are the pHs of the buffers that you can make with all of these. So we're looking here at benzoic acid at 4.2. You know, we could make a really good buffer that's very specific. It has a pH of 4.2 if we took sodium benzoate and benzoic acid in equal amounts and put them in water. Or if we started with benzoic acid and titrated with sodium hydroxide to half of the endpoint, we'd have a pH buffer of 4.2. Okay. If we didn't want 4.2, but we wanted 4.0, we just add a little bit more acid and we convert it over to benzoic acid, and then we can adjust it to 4.0. So that would still be a pretty good buffer. It would be weak on the acid side because it's on the acid side of 4.2. So if you were to add more and more acid, then eventually it would fall off and go, you know, the pH would drop dramatically. But it's got a long way to go on the basic side. It'd have to go past 4.2 and then get away from 4.2 on the high pH side before it fell off and went up to high pH values. And so you can see that in this curve. You know, if we're right here, let's say we're on the acid side of 7.2, if I'm adding acid, it'll go a while before the pH changes, but then it'll drop off. And so where it starts to change dramatically, that's sort of the end of the buffering region. I have quite a ways to go adding strong base before the pH jumps up, but this might be the end of the base region. So this buffer region is surrounding that 7.2, and so this range of amount of base it can take before the pH changes, say, one value or half of a pH value, would be the buffer capacity. So we would choose an acid with a pKa close to that desired pH. And so let's practice. How would we, like, which acid should we use to create a pH 6 buffer? What are our options? Pardon? I can't quite see. Oh yeah. So this one's 5.23. Okay, so that's, you know, what is that? 6 minus that is going to be 0.77. So that's 0.77 low. Okay. What other options? There's lots of options. Hydrogen sulfide. Yeah, so 7.05. And we're looking for a pH 6, so that's 1.05 high. Okay. It's pretty hard to move the pKa, a whole pH unit, and still have any buffering capacity. So you're kind of reaching the limit of it. And so being a one whole pH unit away is going to make it a weak buffer on whatever side you're on. So if we're at 7.05 is the pKa. If we add enough acid to get it down to 6, a little bit more acid, it'll fall off the cliff. Okay? It has a great buffering capacity against base, because if you're adding base, the pH is going up. It would have to go through 7.05 and then have to go like to 8 or 8.5 before it started jumping up. So you could do it, but it would be weak on the acid side because we're below it quite a bit. What else? Citric acid, pKa 3. So this one is only 0.4 away. So it's 0.4 high. And that's a good one. In fact, that might be the best one in the table. There's nothing else that's going to be closer to 6. This one is 6.76, so it's 0.76 high. So we'll be on the acid side of the third proton of citric acid, but only by a little bit. And so it ought to buffer against acid or base. Do you understand my terminology? If I add strong acid, it doesn't change the pH much. And if I add strong base, it doesn't change the pH much. That's what we mean by buffering, because we're in that flat part of the pH curve. If we go too far, then it tips up and goes past an endpoint. So, yeah, so that would be the citric acid. So 3 of these protons come off. So I'd have to go find the structure for citric acid, but this would be the C6 H6 O7 2 minus plus water gives C6 H5 O7 3 minus. So that's the reaction. And so this is the acid, and this is the conjugate base. Hopefully that helps you think about the acid and conjugate base. They're always related to each other. Those are the 2 species fighting over the proton, right? If it gets the proton, it becomes the acid. If it gives it up, it becomes the base. They're paired with each other. Okay. Notice how water and hydronium ion are also paired. So in this case, water is acting as a base, and this is the conjugate acid for water. So it's always this fight over the proton. And so this, so if you were able to find in the store trisodium citrate, then you could buy that conjugate base, put it into solution, and then titrate with acid until you got to a pH of 6. And so that would be a way to make the citric acid on the third proton. You buy the trisodium citrate, or you could start with citric acid and titrate past the first endpoint, past the second endpoint. You get into that third buffer region, stop when the pH equals 6. And so that'd be another way to make a citric acid buffer with titration equipment.
So, like to create a buffer for like a strong acid, you use a base, right?
Yeah, and so the strong acid, because it's a strong acid, it totally dissociates. And so it's going to just give you all of like HCl. You put in a mole of HCl, you produce a mole of hydronium ion, and there's no buffering region. So you would add a weak base that would fight for that proton and create a pKb or pKa, and you would find in that pKa region, that's where the buffering would take place. So it would be the weak base and its conjugate acid that are actually the buffer. And
there's a question on one of the homeworks where it's asking for like
which pairs can make a buffer. Okay, yeah. So what you're doing, that's kind of what I'm trying to address here. So we could make this buffer 2 ways. We could start with citric acid, which is a weak acid, and mix in trisodium citrate, which is the weak base, and that's the acid-base conjugate pair, okay? Or we could put it in with a strong base, and that would turn some of that citric acid into its conjugate base. So there's 2 ways. When you mix it with a strong acid or a strong base, you're actually converting the weak acid into its weak base. Yeah, that's why it's both. If you look at the answers, you could make it with the conjugate base pair, or you could make it with a strong base and turn some of the acid into its conjugate base pair. So it's the titration method that I'm talking about that allows you to do that. So we could titrate with strong sodium hydroxide or strong HCl. And when you do that, you're converting some of this citric acid into its conjugate base, because the strong base is going to rip that proton off. Let's do another one. Okay, so let's go back to here. Let's look at this table. What if I wanted a pH 7 buffer? Lots of options. pH 7. I hear some, but I can't quite hear what you're saying. Hypochlorous acid. Okay, here's one. Hypochlorous acid. That's good. It's 0.4 high. What else? Sulfurous acid, second proton. Okay. Benzoic acid. Don't forget to go below. Like here, 3.75. That could do. Oh no, we're talking about pH 7. Sorry, never mind. Here's a 6.76. That could come up to pH 7. And then I'm doing 4s. I don't know why I did 4s. So yeah, 6.76 could come up to pH 7. Did I get all of them? Hydrogen sulfide? Yeah, this one here, 7.05. So that's beautiful. Now you have all of these options. Hydrogen sulfide is definitely the closest one to 7. Why might you not want to use that? No, it'd be great as a buffer, pH 7 buffer. But this is where we have choices, and now other factors come into play. Now, these aren't things I would test you on, but in reality, this is the things you would think about, right? H2S would be the best choice for pH 7 buffer, but in reality, it's a poisonous gas. Okay, so you wouldn't want to use that because some of it's going to come out of solution, and it smells like rotten eggs. So you would not want a rotten egg smell in the lab that's also toxic and creates nerve damage and all those kinds of things. So probably off the table. Numerically, looks great, but there's other factors involved, okay? And so that's the reason why you probably wouldn't want to go with that one. But if we're just doing a numerical exercise, that's the best one. It's closest to 7, okay? But always be careful, look at these, and that's why we have the MSDS sheets, Before you go starting to make one of these pH buffers or whatever, pull the thread on all of those things and say, do I even want to use this compound? Okay. So let's say we use the sulfurous acid pH 7 buffer. We wanted that second proton on the sulfurous acid. So it has that pKa2 of 7.2, and the Henderson-Hasselbalch equation is this. So what is the ratio of base to acid that we want to use? So here we got some algebra for you to do. We know we have the pKa of 7.2, and we want to make a buffer of pH 7. So we're just now solving for a different thing. Instead of solving for the pH, we're solving for this acid-base ratio. So we move the 7.2 over, the difference is negative 0.2, and we've got to get rid of the log. So we take the anti-log, and so that's 10 to the minus 0.2 is that ratio. So if we know the acid concentration, we can calculate the base concentration. So if we go by the acid and we make a certain solution of a certain concentration of acid, then the base concentration needs to be 63% of that, or 0.63 times that acid concentration. And then that'll be a buffer that gives us a pH of 7. But notice this is this equation. It's one equation, but there's two unknowns, right? The acid and the base. So we get to choose. We get to choose. If our acid concentration is 0.1, because that's what we want to make, then our base is going to be 0.0631. So you choose one and then you calculate the other. But we could choose a different way. We could have chosen 0.01. Like if we had a really weak acid solution, 0.01, let's say this is a really expensive material. We don't want to waste it. We just make a really low concentration. Then our base is going to be 0.00631 molar. Or what if it's a cheap material and we make a 1 molar solution and then our base is 0.631? So that's pretty straightforward. But do you see how your recipe can vary because you have this relationship of acid to base, but it doesn't tell you the specific thing to use? Now, let's focus on these three. Which one of these would resist the change in pH the longest? Remember that acid-base reactions are stoichiometric. So if I put in sodium hydroxide or if I've got a buffer and my little critters, my bacteria are producing acid because of the little redox reactions. How long, which one of these will go the longest before the pH changes to where the bacteria all die? They all have the same pH.
Is that something you have to look at the half-life for?
No, it's just we have these 3 different concentration magnitudes. Which one of those is going to last the longest if my bacteria are constantly putting out strong base? The middle one, it's got the lowest value of these. And remember that the acid-base chemistry is going to be stoichiometric. And so when, let's say then the bacteria put out 0.01 moles of their little base per liter, so it'll totally wipe out our acid, and we won't be in that pKa region anymore. So we'll wipe it out with 0.01 moles. Look at the top one. It'll last 10 times longer. If the base has, the little critters have to put out 0.1 moles of base per liter solution before that gets out of the buffering region and starts to dry out. So you were right, it's one of the extremes, but it's the bottom one. Now the critters have to put out a whole mole of acid before they leave the buffering region and reach the endpoint. In fact, that's when it would reach the endpoint. But somewhere before that, it's going to take more of that bottom recipe. And that's what we mean by buffer capacity. So how much strong base? The bottom one can take, say, a mole of base, and the middle one can take 0.01 mole of base before it's really out of whack. So that's what buffer capacity is. So I asked, which of these potential recipes will resist the pH changes the most? And so since this reaction with strong base is a limiting reactant problem, we're going to run out of a reactant. As it puts out a little bit of base, that base runs out. Puts a little bit more base, it runs out. But we're chewing away at the acid every time that happens. And so the bacteria can put out a lot more base and chew up this amount of acid. Same with the acid. Let's say the bacteria puts out acid. It's going to be chipping away at this conjugate base every time it puts out acid protons. And it's going to run out of this one last. This is going to last the longest compared to this or compared to that. So you see there's 2 things related to buffering. One is the ratio of acid to base. That tells you the pH. And then the other is the magnitude of the acid and the magnitude of the base. How big are both of those numbers? We get the same ratio with little numbers or big numbers. And the bigger numbers have a higher buffer capacity. See, all 3 of these solutions have a pH of 7. So it's no longer about what pH it is. It's how long will that pH last as I'm adding in acid or base. And so you need big numbers at the correct ratio to get a good buffer solution. So let's come up with a recipe for this. So if we want to go with the 1 molar acid and the 0.631 molar base, how do we actually create this buffer in the lab? Okay. So what's the acid species for the second pKa? So help me out. We have the sulfurous acid, that's H2SO, and how many oxygens do I have in this one? It has the OUS ending.
4? Oh, wait, 3.
3, yeah. Sulfuric acid has, X have more oxygen than Us's. Okay, so sulfurous acid is H2SO3. And so we're at the second pKa. And so what's the acid species for the second pKa? H. We're going to just be pulling that second proton off, so there's only one H left, SO3 minus. So that's going to be the second proton that comes off. That's the acid species. The first one is the first proton. It comes off, and then we're working on the second one for the second pKa. What's the base species for that? So if I pull that proton off, I'm left with SO3 2 minus. So if we had a chemical store that had every known chemical in it, we might be able to find a sodium hydrogen sulfite and a disodium sulfite bottles, and mix those in solution at the appropriate concentrations of 1 molar and 0.631 molar. And that's probably not going to work because you're probably not going to find those two bottles. Okay, so so how do we get there? Well, this is, and I added a little complexity to the recipe. I don't think you have some of these lines here, but if we want to make that 1 and 0.631, then we need to take into account the dilution of these particular substances. Now, look at these numbers. I'm multiplying the concentrations by 2 because when we mix the 500 mils and 500 mils, the volume is doubled. And so they're going to get cut in half. And we'll see this on the next page, the ice table. Okay. And so how do we get that amount? This 1.631 moles per liter of solution times 2. So really it's like a 3.2 moles of solution of this. We could find that sodium salt maybe, or we could use sodium hydroxide. And so to get 500 mils of this concentration, this is what you would mix together. And if you want to show me this calculation on your homework, then that's a great thing. I'm really treating you like adults here and saying, you want that? Do this. And I'm not walking you through every little bit of the math. It's just 2 dilutions in a mixing and an acid-base reaction. So you verify to yourself how mixing 250 mils of this concentration to 250 mils of that concentration gives me 500 mils of that double 1.63, so the 3.262 molar HSO4. Okay, so that I'll leave that to you for your homework. And then we end up with 1 liter of 1 molar acid and 0.06 or 0.631 molar conjugate base with a pH of 7. So let's look at the math of just the buffer piece. Okay. So if we have 500 mils of 2 times 1.631 molar solution of the HSO3 minus, and we mix that with the 500 mils of base, we've diluted it by half, and we end up with 1.631 molar HSO3. If we do the same with the base, only now we have 2 times the 0.631, 500 mils mixed in with 500 mils, it's diluted by half, we have the 0.631. Okay. And then this is strong base, and it rips that proton off and makes the conjugate base here. So we're making the conjugate base by adding strong base. So do you see, this is that problem. Do we have to find the sulfite anion, like disodium sulfite, or can we just add sodium hydroxide? And we're adding sodium hydroxide, and we're getting the sulfite ion. So you could add the sulfite ion, or you could add sodium hydroxide. And so this is the sodium hydroxide method. We're going to take this down to 0, use up all the sodium hydroxide, and produce the 1 molar solution of the acid, the weak acid, and the 0.631 molar solution of the sulfite, the weak base. And then we get our pH buffer. Okay. So the reason I say up here, add slowly, this is the one physical hazard you have when making buffers, is especially if you're using strong acid or strong base, when you mix these, the acid-base reaction is exothermic, and so it can generate a lot of heat. And so you just got to be careful. Sometimes, like if you add water to acid, or you've got strong acid, the heat is enough to boil the water, and then it sprays. It boils, so it bubbles, and it sprays concentrated acid on you. You can get in your face, get on your clothing, get everywhere. And so you always add acid to water, not water to acid. Or you add more concentrated things to less concentrated things, so that as soon as that concentrated thing goes into the less concentrated thing, it's immediately diluted. And yeah, there's an exothermic reaction there, but it's the heat's being taken into the bulk solution of the dilute solution, and just go slow. Okay, now the rest of today is just sort of information, factors affecting solubility, and buffers in equilibrium, different kinds of equilibrium. So it's just some interesting facts. Now, there were some questions on the homework, and there's a couple on the test about which of these precipitates will be pH sensitive. I think on the homework it was the HF one, right? You had some chloride or whatever, some fluoride, and then calcium fluoride was the one that was pH sensitive, and that's because the fluoride anion is the anion of a weak acid. And so as soon as it comes off of the chlorine, it's going to grab a proton from water. If I have that in basic solution, it can't find a proton, and so it's going to stay with the calcium. If I have that in acidic solution, it's essentially like Le Chatelier's principle. I'm pulling on that fluoride ion. As soon as it comes off the calcium, it finds a proton, makes XF, and then the calcium has no fluoride to find, and so it'll dissolve. And so you can actually undo one of these precipitates with pH if the anion is a weak acid or a weak base. So basic anions like sulfate, phosphate, acetate, and especially hydroxide are pH sensitive, and this is the big one here. So if you have any hydroxides, those are very pH sensitive. Here's a picture of that. We have magnesium hydroxide in solution and precipitating out. And so you have those hydroxides. But if we start to add acid, then as soon as that hydroxide comes into solution, it finds the free protons or the hydronium ion and reacts. And so then you come over here and you just have magnesium ion and water, because we added enough acid to get rid of the hydroxide, and so the magnesium hydroxide can't precipitate because the hydroxide's gone. So that's very pH sensitive. You put magnesium hydroxide into acid, it'll dissolve. And likewise, if you put it into base, it will crash out. And so if you put it in high pH, you can precipitate out magnesium. Sometimes you can have what we call coordination complexes. So here we have silver chloride in solution, nice beautiful crystalline substance here. You've got very few, but some silver ions and chloride ions in solution. But we calculated that a couple of times ago. It's very small, like 10 to the minus whatever molarity, really small. But there's an equilibrium there. And some of those silver chloride ions find each other and precipitate out, while some others dissolve. If we can mess with that equilibrium by grabbing a hold of the silver ions in solution, then the return trip is blocked, and the silver won't precipitate out with the chloride because we've capped it with something. And so that's what we can do with ammonia. So if you notice the silver chloride, this is AgCl solid in equilibrium with Ag plus and Cl minus. And that's in equilibrium. And it's mostly to the left. So it's mostly silver chloride. But if we can take this silver and cap it with an NH3 on either end, we have this coordination compound. That silver's a +1 anion, or +1 cation, and this forms a complex. And it's not a covalent bond, but it's also not really just a van der Waals stickiness. It's a coordinated compound. Those lone pairs are interacting with some orbitals on that silver ion, and it's a pretty strong connection in solution. So look what this is doing. This is Le Chatelier's principle. We're pulling on that silver. And so what happens to the reaction? It shifts to the right. And so we can get all of this silver chloride to dissolve if we add enough ammonia. If we add a 2-to-1 ratio of ammonia to silver, then we can get it all to dissolve. And we'll have formed all of these little ammonia silver complexes in solution. And the chloride just can't find any free silver to precipitate out with. And so this is a factor that affects solubility. And it's not pH related. There'll be some pH in here because of the ammonia is a weak base, but it's really this complex ions. And so this is an acid-base reaction, but it's a different kind of acid-base. It's a Lewis acid. So a Lewis acid is an electron acceptor. And so in this case, the silver is acting like a Lewis acid. It's accepting those electrons, and the complex ions are Lewis bases, the electron donors. So the ammonia is donating those electrons to the silver. And the silver is interacting with them. Okay. So this would be a Lewis acid, Lewis base interaction. We're not going much into this. If you're a chemistry major, you make yourself up into inorganic chemistry. This is a huge area of inorganic chemistry. So you'll get to know more about Lewis acids and Lewis bases in inorganic. But look at these various reactions. You have the reaction here, chromium, cobalt, copper, nickel, and so on. And here's your equilibrium constant. This F stands for formation. Everything's aqueous, so we have products over reactants, and so you can write out all of this. Let's do this one for the chromium. Okay. And so that would be the equilibrium constant expression, and that's the formation constant, and that would equal 8 times 10 to the 29th. Big number. So which is predominant in this reaction? Reactants or products? So that's a review question. You got K is equal to 10 to the 29th. Pretty big. So this ratio is equal to 10 to the 29th. So of these three numbers, which is the biggest? The top one, right. It's way bigger than 1. 1 would be top equals bottom. Okay. So 10 to the 29th, that means the products are favored. That's a strongly favored complex. Notice how we have a lot of these things. We have ammonia here. We have cyanide ion, so CN. We have SCN, so thiocyanate. We have hydroxide, bromide, thiosulfide. So we have all of these things. These different ligands will interact with the metals, and they give you the most amazing colors. And so that's the fun part of coordination chemistry, is the colors of these D elements. So all of those elements in the middle, you see we're talking about chromium, cobalt, copper, those transition metals. When coupled with these different anions in these coordination compounds, they almost always give you a different color. It depends upon the anion you stick on there. And this is how the ancient pigments were made. So clays were inorganic compounds that had trace metals in them, and they would have a basic clay, or maybe they found a deposit of ammonia or something like that, and they could get a different color. And so that's one way they tell if this ancient piece of pottery is a fake or not, is if the colored compounds aren't these inorganic compounds, then it's a modern forgery. If it's a latex paint, then you know it's not an ancient pot, because this is the only colored substances that they had access to with these different inorganic dyes. There are some substances that are soluble in acid, soluble in strong base, and they precipitate in the middle regions. And aluminum is one of those, like aluminum hydroxide. So in strong acid, there's no hydroxide left, and so you have aluminum ions in solution. So they're surrounded by water. In strong base, you've got some base ions on there, and then the aluminum hydroxide can also act like a base, and it can So you have a mixture of aluminum hydroxide and aluminum with water around it, and that's soluble. But here in the middle, you've got just the right amount of base, the right amount of water, and you've got an aluminum structure that will precipitate out. And that's what's being shown here. So this is kind of cool. This is aluminum dissolved in an acidic solution, and then you drop in some strong base, and it precipitates in the middle where the pH is in between the acid and the base. And so up above you have strong base, down below you have strong acid, in the middle range you have the precipitate. So it's kind of a cool demo. And so always think about that, Q and K. If you can calculate Q, then you can compare it to K and determine, is my Q less than K? If it's less than K, the reaction is going to go forward. If I run out of solid, then no precipitate forms. If Q is equal to K, it's at equilibrium and the solution is saturated, and that means you're going to have some solid in solution. If Q is much, much greater than K, then the salt will precipitate. It'll run that reaction backwards until you get to K, the equilibrium constant. This selective precipitation of ions is the way that they did this in the past. Like, this is an ancient scheme. We were at a garage sale and I saw a box of books and they looked old, so I started digging through them and I found an 1898 book of analytical chemistry, quantitative analysis. And in the back was a flow chart, and it was this flow chart, 1898. And so think about this. If we take a solution that has all of these ions in it and we add 6 molar HCl, we're going to precipitate out silver, mercury 1, and lead 2, because those are insoluble with chlorine. Everything else, all the other chlorides, are insoluble. But this is a way to remove silver, lead, and mercury 1 from our solution. And then all those remaining cations are still in solution. How do we separate those? Well, we put them in a centrifuge, make sure the precipitate's nice and packed, and we just pour off the top. And so we've separated the silver and the lead and some of the mercury. Okay. Then we add H2S. So if we had H2S in the lab and we bubbled it under the solution, it would react with some of those cations in a mildly acidic solution, and it would produce all of these insoluble sulfides. So copper sulfide, bismuth, cadmium, lead, mercury 2, arsenic, antimony, tin. So we could pull out this group 2 with the sulfides. So we pulled the chlorides out first, then we pull the sulfides out next. Then we can react that with a basic solution of sulfide, this ammonium sulfide, and we can get out some of the hydroxides, okay, and some of the remaining sulfides. And then we could add this with phosphoric, with the phosphate salts, and we could get out all of the phosphates that precipitate. And if you don't do this in order, you'll pull out some of the others with the phosphate group and maybe mess things up. So this is a particular order that's been discussed or determined since the 1800s as to how to separate the most ions in the least amount of solutions. Okay, and then the last one, the ones that aren't soluble in anything, essentially all you have left is the alkali metal, the sodium, potassium, and ammonium. And this is the scheme that Marie and Pierre Curie used to find the radioactive elements and win a Nobel Prize. So just acid-base chemistry and precipitation was enough for them to do. I mean, talk about grunt work. I don't have to read all of this, but they discovered polonium and radium. Now, how did they know that they had a new element? They knew that pitchblende contained uranium, and they had purified amounts of uranium, and the uranium was, say, this radioactive, but the pitchblende had that much radioactivity in it. So they said there's got to be something else in there that's radioactive. And they used this precipitation scheme to narrow it down. Now, how do you know? Well, you go through this and you do the precipitation, you separate the liquid from the solid, and then you stick your Geiger counter on the solid. And then you stick your Geiger counter on the liquid, and they say, the liquid, it's still radioactive, the solid's not. So we know our new element is in the liquid. Then you do the next step, and then you look, now it's in the precipitate. And so then you know it's now your new element is mixed in with, say, 5 or 6 elements, and then you work your way through it. And they were able to purify it that way. So they probably here, they did it in 20 kilogram batches, 40-pound batches. Think a 40-pound bag of dog food. I mean, that's how much they were grinding and dissolving and precipitating. And they had like a truckload of it. And so they had a truckload of this stuff just dumped on their doorstep in their lab. And they would just take 40 pounds at a time, grind it up, dissolve it in strong acid, start precipitating it out. That is brute force chemistry. And yet they hammered their way through it and discovered 2 new elements. So kind of a neat capstone on how to use equilibrium. This is old school. Now we run it through a mass spec. You need about that much. In fact, if you can see it, it's too much. And so it's much easier now, but props to them. So y'all have a great day.